Good afternoon, ladies and gentlemen, and welcome to the SAIEE KZN Centre's latest webinar on lightning threat management, what has changed and what will change. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. And by default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel under the KZN Centre playlist. This channel is updated regularly, so ensure you check back as often as possible for new uploads. In the chat box, you will find a link to subscribe to the SAIEE TV channel. Please, I encourage you to do so. It is for free. And of course, you also find information on how to become a member of the SAIEE to start reaping the benefits, as well as see the latest updates of our SAIEE Training Academy's calendar. A certificate of attendance will be issued a few weeks after this webinar, once we have received the CPD validation number from EXA. I'd like to now introduce you to our host for this afternoon, Mr. Shepherd Nkosi, who is the chairman of the SAIEE Kwa-Zulu Natal Centre. He holds a Bachelor of Technology degree in Electrical Engineering, a post-degree with USQ, University of Southern Queensland, Australia, post-degree in Project Management with the University of Stellenbosch, and is currently completing his master's degree, MSc Electrical Engineering with UKZN. He's chairperson of the SAIEE KZN Centre and served as vice president of the Durban University of Technology Advisory Board and is professionally registered with EXA. Over to you, Shep. Sorry, Shepard, just unmute yourself.
Oh, thank you. Thank you so much, Madam Afrabus. Thank you. A warm welcome to one and all. We're happy to see you connected remotely and to be ready to join us this afternoon. I'm sure you're looking forward to hear from our guest speaker. But before we introduce our guest speaker, I have Dr. Stephen, who is with us this afternoon from the KZN Centre, and is the past chairman of the SAIEE KZN Centre. And Dr. Stephen was born in Joburg, South Africa, so he's a South African member, and he holds a BSc, MSc, and MBA degree, and also a PhD and in overhead line design. He retired from Eskom 31 Jan 2020, where he held the position of Master Specialist in the Technology Group, responsible for distribution and transmission technologies of all voltage, covering both AC and DC. He was responsible for the smart grid strategy for Eskom. He is he also holds a position of group capacity capital program manager, responsible for the electrification and capital projects with 12 billion per annum. He also was the international president of SIGRI from 2016 to 2020. So he's the first African to hold this position. He's a fellow of the South African Institute of Electrical Engineers and was awarded the President's Award in 2016. He's currently a specialist advisory or advisor at the UKZN, that's in Devon. So where he also developing courses and online design, supervising postgraduate students, and advising and assisting research in research matters. So I'm happy, members, to introduce Dr. Stephen, who will be assisting me with the question and answer session. But who's our guest speaker this afternoon? Thanks, Dr. Stephen. And who's our guest speaker this afternoon? We've got Richard Everett, who's National Director from ELPA, Richard as I've indicated, is a national director from the Earthing and Lightning Protection Association of South Africa, and he is an SAIEE member and an SAIEE Lightning chapter office area with a BSc in electronics engineering, MSc in electrical engineering, and his PhD doctorate on lightning risk and progress. So Richard has experienced and addressed a wide range of challenges over 31 years in the power, utility, and lightning protection industries. These challenges were overcome by collective engaging with skilled leadership to implement sustainable lightning resilient solution. That's our guest speaker, Richard. I think I would like to also maybe repeat the theme that Richard will be sharing with us, lightning threat management. What has changed and what will change? Richard, you have our undivided attention. Over to you. Thank you.
Richard, just unmute.
I was just practicing my voice. Just practicing my voice.
Great. All good, thanks.
Thank you, Shepherd, and Rob, it's good to see you again. Thank you, Minx, and ladies and gentlemen, it's an honor to be presenting this material, and I hope I do it justice. We still have a lot to do, so I kind of, let me just get stuck in. So the subject today is really to kind of highlight that lightning on its own, having lightning information on its own and not knowing how to apply it or apply it incorrectly, misinterpreting the information can in itself cause more problems and makes it more difficult for us to justify any expense in doing any remedial work. So the extent of what has changed, we've been challenged over the last 36 months probably, and probably a bit more than that in terms of needing to make changes to our standards, but we've had some challenges with our infrastructure, and that's pretty much why ALPA as an association has been established to bring some framework in so that there's synergy between the associations in support of the industry and our governance organizations. I just thought we should probably start with an understanding of lightning and what lightning does and how we would misjudge the issues. The slide I've got up, sorry, can I just confirm everybody can see it? I'm Minx? Richard?
Yes.
Richard, yeah,
yes.
Talking to myself.
Yeah, thanks.
Thanks, Shepherd. Okay, so this is an incident where the filling station at the Lower Selby rest area in Kruger National Park burned down on Saturday night. It's believed to be lightning, and so this is an incident five days ago that on the left-hand side is what it used to look like. This is on the left-hand side is the main entrance into the rest area. The shot on the left at the bottom is the actual filling station, so it may sound like a big to-do, and when you look at some of the damage, the photographs are a little bit up close. It's a fairly small site. You can see there's no mast, there's no lightning protection. The image in the middle is on about 8 o'clock on Saturday night. A visitor took a little video of this building burning down. Very fortunate, it is a fueling station, so there is fuel, diesel and petrol there, so very fortunate that it didn't explode. Image on the right, as they managed to get it all under control, the thatch is all gone. And then what we have left on the right-hand side is pretty much total destruction. And it's very interesting to see the announcements from the communications people from Sandparks trying to just assure people we're doing the best we can. And so at this stage, the filling station is still not open yet. Imagine it's going to take a little while to get it back open, and this is a small entity compared to our industries across the country. Another example, in November 2007, when the Engen oil refinery, a tank got hit by lightning. It burned, because it's fuel, so it burned right through the next day, and you can see that there's really not much left of it. I'm going to, as we go forward, just focus on a more slimlined example, but more detailed. But in terms of the overall presentation, I'm going to be walking through the backbone being our standards. So I'm going to cover lightning in the global electric circuit of what we have as a planet, and where we may want to tap off on this energy. I would wonder what happens if we tap off that energy, and then it reduces the impact on the global circuit. So it's probably a good thing that we can't tap off that lightning discharge at this time. Then I'll just go through the behavior of lightning as it's specifically impacting on our threat to us as people, our services, the structures, and our assets. Then I'm going to look into the actual cloud to ground lightning activity, which causes the most inconvenience to our industries, to our country. I'll walk through a step-by-step, just unpacking what happens to the cloud to ground stroke as it approaches a building of value. And I do want to emphasize the word of value, because we seem to either completely want to disregard the analysis and to understand our risk and managing the risk, and we just want to plug and play, or we just want to walk away from it and say it's not a big deal, or we want to over elaborate and we want to implement a Mercedes when a little Beetle will be just fine. So I'm going to go through the basis of the formulas and throw in some numbers just to see the impact if a building doesn't have a lightning protection system or surge protection measures in place. And then from there, I'll go into the overall risk management, kind of just consolidating is the with and without lightning protection, and then just differentiating these concepts of a lightning protection system from surge protection measures, where together they offer us a lightning protection in total. So we get lightning protection made up of lightning protection system as well as surge protection measures, and which hasn't been common discussions in the past. And then just a thought on the surge arrestor side, how we think we understand surge arrestors, but we may not. So I've taken this drawing straight out of the SAN 62305 Part 3, which is the physical protection against lightning, physical damage to structures and life hazard. It's a multi-story building, and illustrating at the bottom, we're just so you can make head or tail of this drawing in isolation, ground level, earth at the bottom. This is the global electric circuit, where we take all the environmental things into account. Actually, let me just get straight to the lightning side. We have multiple layers in the lower atmosphere, middle atmosphere, and the upper atmosphere. But just bringing it just back to lightning, this is what we've got with an electrosphere, approximately 60 kilometers above the Earth's surface, surrounding the Earth, and we have about a 300 kilovolt voltage along that electrosphere surface around the planet. And we have an ongoing electric circuit whereby in fair weather conditions we have leakage current. We're at ground level about 100 volts per meter, so it's not 300 kilovolts over 60 kilometers evenly. It's graded, and we have at ground level about 100 volts per meter. We have our lightning activity with the charge buildup in the clouds, where that effectively then provides us with a electric generator. So on the whole system, we have about 2,000 thunderstorms taking place at any one time, covering at least 10% of the Earth's surface at any one time. And the lightning charges, the lightning within that circuit actually charges the circuit, and hence the term it's been called a global electric generator. The significance of this is that if we didn't have lightning activity taking place at this rate across the whole planet, that electric field that we have would dissipate in a matter of about 10 to 15 minutes with no electric field at all. And the impact of that, I won't go into that. So this is where you see that the lightning acts as an electric generator, and as a consequence of it, we really don't have a choice of trying to do away with it or push it somewhere else. It is part of our planet, and it's part of our makeup, and it's not a risk that we can just wish away, or at some stage we'll come up with the technology and we will eliminate it, as we are wont to do with all things. So just going into lightning behavior, taken a Encyclopedia Britannica image, as well as Rakov and Martin Human extract from their book. The illustration here of the storm activity, see that the positive and negative charges. Actually, let me just stick to my slide. So with all our lightning activity, about 90% of all lightning activity remains in the air. It is cloud to cloud, between clouds and intra-clouds, but intra-cloud and inter-cloud lightning activity. So you'll see abbreviations of CC, cloud to cloud lightning, or IC, intra-cloud or inter-cloud collectively. What's interesting here on the right-hand side, you see a discharge just going out into the air. And if we fully understand electric fields, it makes a lot of sense. As the further you go away from the charged item, the electric field dissipates until eventually you don't have the capability to have ionization and avalanche stops. My background in Eskom with transmission and distribution was very much on the power lines, so it's kind of a natural migration. In terms of so all cloud to cloud lightning activity is about 90%. Cloud to ground activities only about 10% of all lightning activity. Now we have there is another webinar taking place on Tuesday, being coordinated by the Lightning chapter, SAIEE Lightning chapter. If you haven't registered for that yet, I would recommend you do. But just talking about lightning data and accumulating lightning data, that webinar will go a lot further. But the data that we're getting, that we have currently, showing about 25 million cloud to ground lightning strikes taking place every year. So it's on average from 2006. So we're looking at nearly 20 plus years now. Given that we have 25 million cloud to ground lightning strikes, you can do the maths as to how much overall lightning activity there is. So just further characterizing the cloud to ground lightning activity is it has direction. We have both upward and downward lightning activity. The lightning has polarity, positive and negative, depending on the extent to which the fields build up to have breakdown. You'll notice in this image on the top right is the positive charge within the cloud is very much predominant at the top of the cloud, whereas negative charge is predominant at the bottom of the cloud. This image is slightly skewed, but it does, from time to time, you see this small center of positive charge, extremely small, such that 90% of the cloud to ground lightning activity downwards is 90% is negative because of the smaller clearances at the bottom of the cloud as opposed to towards the top. Okay, then we also have upward lightning activity, both positive and negative, and you'll see that both percentage-wise are really, really small, and it only happens because of tall structures on the ground. So as again, the webinar on Tuesday, you'll see discussions about monitoring lightning activity to the Hillbrow Tower and to the Brixton Tower. I'm sure there's Telkom and Centec towers. So just a brief overall view on the formulas related to this. Formulas can get messy, and I don't function very well when I look at a document that's got 1 million formulas in it, but it's pages and pages of formulas. So what I've just put up here is the key components that when you are looking at assessing the risk of lightning at any part of your assets, these are the components that you must be able to interpret. So we've got charge, Q in coulombs. We've got work, energy absorbed, and absorbed in power system, we would call that as losses. In lightning, it's energy that is absorbed within whatever medium the lightning current is trying to go through to get to ground. The time is very significant. The rate of rise and fall of the surge of the lightning transient. Of course, then we've got electric current, which is in amps, but it is also as a formula. So there is a formula on the top left. So these blue triangles really represent formulas where charge Q is current multiplied by time. And if you were looking at current, it would be charge divided by time. So that would be amperes is the same as coulombs per second. It's a neat little visualization to help you remember issues. Then going into power, where we have power is watts, but it is also joules per second. That is power with the work divided by time. And then we have voltage, which is the electric potential, and it's also go to the joules per coulomb, which is voltage. Here, this triangle over here, oops, sorry, where voltage is work divided by your charge, joules divided by joules per coulomb. Right, then into the key components for lightning is we've got lightning as a current source. I'll pick it up in the next few slides, but whenever that current is trying to, that charge is trying to go to ground, we have a current flow through the medium. And inevitably, it's never zero, so we have a resistance, but we also have an impedance, as Prof. Chanda Magames will tell you, that we need to just keep in mind that many of our channels and systems that we use has reactance. So with inductance and capacitance and lightning as a high frequency component, it's important that we understand that as a reactance, inductance is, or the inductive reactance is a function of frequency as well as the size of the inductance, whereas capacitance is the inverse of that frequency and capacitance. And the significance of that links back to the behavior of an inductor, that it's not just simply that there's current flowing through and therefore you will have a voltage. What is happening is as your current increases or decreases, the rate of change of that current in relation to the inductance causes a voltage. So that is why the time change of the lightning current flowing to ground is important. So in essence, then what we need to understand is the concept that we have is that the charge, within the cloud, charge is building up. We're having a transfer of charge. So in that context, we also then need to understand that for cloud to ground lightning, charge is being transferred from cloud to ground, which means we have coulombs per second, which is amps, and that straight away puts us in this. There is often a discussion and debate about whether lightning is a voltage source or is a current source. You know, that lightning strike, what was the actual voltage of that lightning strike? Well, it's quite easy. Well, it's simplistic in the sense that we have charge transfer, exactly as you can see on the screen. We have charge transfer over time. That translates to current. The current flowing through whatever resistance or impedance we have produces a voltage. So when somebody talks about it was an enormous lightning strike that we had 2 megavolts or 100,000 volts, that actually doesn't tell us anything about the lightning strike. What it potentially tells us is that the resistance that lightning strike had to pass through was quite high. So immediately there are some fundamentals that's not very difficult to understand, provided you stick to the basics of our science. And just in that context, to understand this concept of coulombs with charges, this Coulomb's law, just understanding the extent of the force that sits behind lightning is if you take two charge particles, put them 1 meter apart, charge each one with 1 coulomb, you end up with 1 billion newtons. Now, I've never really, I'm not really sure whether it's 1 billion newtons or 10 billion newtons, but when you put a B in there, it's just it's really immaterial. We need to be staying far away from it. And the equivalent was said that it's enough to the equivalent force of 2,000 jetliners. I'm not sure whether those are big jetliners or small jetliners. All I know is it's a hell of a big force, and it means that we also need to understand the mechanical impact of whatever systems we put in. So when we are shocked and surprised with the mechanical damage, with bricks blown out of walls and entire structures destroyed because of lightning, this is what we're talking about. So going to the building, if we don't have a lightning protection system, so kind of in assessing whether or not we have actually got any threat, the risk management approach is first understand, is there a risk? Do I have lightning? Talk about ground flash density. How much lightning do I have over an extended period? Just my slides at the end are considerably briefer than I had hoped. So we just bring us in now. Ground flash density is not a number that fluctuates every year. It is a number that must remain constant. It is a choronic cycle, solar cycle. So the movement of the sun, the earth, and the moon around each other develops on average for the last 90 plus years. We see an average 11-year cycle. So once we've got 11 years of lightning data, we can now start talking about another 11 years and do a comparison. So in that sense, when somebody comes forward and says we are seeing an enormous increase in lightning activity, when you understand the principle of ground flash density, you are now in a position to be able to say, if you're seeing sudden increases in 2010 to 2017 to 2021, seeing a sudden increase in lightning activity, something has changed. And if you go to Uppington, where they've got a 200-meter solar tower installed, what you should see, and you should anticipate, an increase in ground flash density, because for as far as the eye can see, day after tomorrow that way, and day before yesterday this side, everywhere it's just flat. A mountain probably rises about 10, 15 meters. So it's a flat area. So that is why the ground flash density in the Northern Cape, in Uppington out towards Springbok is low. Now you put up a tall tower, 200 meters, it is inevitable that you're going to see a change in the lightning activity. So just to appreciate that when we have a ground flash density map and we have ground flash density values, it's imperative as we go forward that that number not change. If that number changes, our science tells us either global warming has snuck up on us and channeled some strange channels through South Africa, or we've got a problem with our measurements, or maybe we're taking the information from the wrong service provider or point of service. Okay, so having said that, the very first item on this list of what I have here of 7 items, lightning current. The lightning current has got nothing to do with the flash density. Lightning current has got to do with the amount of charge that's built up in the cloud, and from summer through to winter, there is obviously we have summer thunderstorms, and during that summer period there is lots of storms, and hence a significant buildup of charge and lots of lightning. But what we need to just appreciate is that it doesn't matter where you are in the country. In the 28 years that I was in Eskom, the last 18, analyzing lightning activity in every part of the country, in 9 provinces, on distribution networks, Eskom transmission networks, in the distribution of statistically distribution of lightning activity on any power line, we found pretty much the same thing. And I apologize for not having that slide yet. I was kind of really getting G'd up to have a full system to present. But what we're seeing is a bell curve, logarithmic bell curve that is peaks around about 9 to about 14, 15 kiloamps, and drops away that's by about 30 kiloamps. The number of lightning strikes within the 5 kilometers of the power line that we looked at, not from the traction radius, but just statistically getting reliable data, it's the same throughout the country. When we start seeing very high lightning strikes, the importance of us trying to determine whether or not we put in a lightning solution, a mitigation solution for that lightning strike, or do we stick with our ground flash density data, which says every year for the last 11 years, this is how much lightning we have. And at the very end, the outliers, statistically, the low, very small number of lightning strikes have these enormous values. So once we've established that that value is in fact correct, what we need to establish is how much money should we be putting down to sort out this problem. If it's only going to happen once every 15 years, once every 20 years, once every 40 years, do I really have an asset management problem? And hence, when we look at the safety standards within, say, safety, I say it with a bit of poetic license, when we look at the margins of error that we can work with in saying 62305, part 2 is the risk management aspect in trying to determine whether or not you need lightning protection. Now, as I say that, what I am saying, and this illustration that you see on the screen here is a building that doesn't have lightning protection. Now, as a guy that's been involved with lighting a really long time, it saddens me, it surprises me that we still have debates about whether or not we need lightning protection. I don't need to remind you, just quickly go back to the first 2 slides, that little thatch roof filling station could just as easily have been the main buildings at that rest area. It could have been at Skukuza, it could have been at one of the others where there is people residing there. It could have been in the middle of December, and a fire, it's small, but within minutes it was in flames. So it's one of the reasons why we need to look at a joint exercise with the lighting specialists from our lighting industry, together with the fire risk managers and fire risk assessors, as to exactly how we should be addressing the issue with thatch roofs. Okay, before I get further digressed in that, let me come back here that we talked about those formulas, and what we have to build this assessment is you've got lightning current, peak kiloamps, the rise time in microseconds, the resistance of the path, so in this case it would be brickwork, also the impedance. If there is any metallic components, it needs to be in series and parallel. Then the distance from top to bottom, because the further it is, the resistance and impedance will increase. And then the amount of energy that's actually being absorbed. And we talk about surge arresters. When you rate a surge arrestor, you rate it for the anticipated energy that it has to absorb as it tries to take all the energy from one side to the other, particularly on our MB, so that in power systems, medium voltage networks, where the practice of putting a shield wire on to try and guide the lightning away from our power system has a contradicting problem in that the insulation levels are too low for that resistance. You kind of keep on coming back to this item that the resistance is a real deal breaker. So with medium voltage networks, if we have a back flashover, back flashovers are typically in the order of nanoseconds, whereas the lightning is in the order of microseconds. Nanoseconds means that DIDT is even faster and causes bigger problems. So we don't want back flashovers and air cap flashovers. So this issue, sorry, bringing us back to this building, without any metallic means by which the charge can be transferred to ground with the least path of resistance, we are forcing 10,000 amps and more into this brickwork. Now, very quickly, somebody will say, "Now, hold on, it's not 10,000 amps. It's 10,000 amps rising at 5 microseconds and then falling away at 100 microseconds. So 200 microseconds, it's come and gone. So it's not 10,000 amps. So at the moment that it's 10,000 amps, all the charge that is in the cloud is going to ground. Whether you want to debate the mathematics of it or not, that energy is going to ground. So all that changes is that's the area under the curve. So we end up with this energy that the building will absorb. Can we afford it? The risk analysis, the identifying just how big this threat is if this is a hospital and you have people on life support systems and other tricky bits that it's not easy to just hop up and run out of the building. It's not possible to think that you can anticipate a storm and then take remedial action. You can only take remedial action if you have a plan in place. So your emergency preparedness plan. Lightning protection is an emergency preparedness plan that needs to be in place. Then we end up with this item of the charge transfer in coulombs. Ideally, well, not ideally, we've got a simple electrical system that what comes in must go out. So whatever current is coming in the top must go out the bottom. Doesn't matter what we do with a lightning protection system or not. So an interesting item regarding brickwork, and I wasn't aware of until I attended one of Prof. Chana Magomez's presentations, is that brickwork has brick and mortar has a characteristic impedance resistance of about 10,000 kilo ohms, so 10 to the power of 5. I might have made a mistake. Yeah, I've got too many notes in there. So it's 10,000, 10 times 10 to the 5, 10 kilo ohms that we're working with. And okay, before I put my foot further in my mouth. So when we start putting real numbers in, I mentioned the peak value of 10 kilo amps. If we're talking about only a single lightning stroke, so typically a first return stroke would have a rise time of about 5 microseconds. So I've conservatively made it less. So we get a smaller number, so you can work out the figures. So with 2 microseconds, the material resistance of 100 kilo ohms, there we have 10 to the power of 5. And we don't have any down conductor system. And I've made this building 10 meters. Now, when we do the calculations, just throwing in those little blue triangles to make things a little bit easier, when we work it out, we end up with a number of 200,000 kilojoules. So that's 2 times 10 to the power of 8. Got that one right. So if this particular building with brick and mortar does not have any mechanical or metallic path by which that lightning current can go to ground, a typical fairly fast rise time of 2 microseconds. This energy absorbed is over time. So the quicker it is, the less energy it will absorb. So if it was 5 microseconds, we would be doubling this to 400,000 kilojoules. That's really not good. When we work out the actual charge that's being transferred, 0.02 coulombs. So fortunately, no jet line is being driven. When we do have a lightning protection system in, now when we're talking about a lightning protection system, it's the mechanical parts of having air terminations on the ceiling, on the roof, air terminations on the roof or somewhere around the building such that it will intercept the lightning strike. Lightning protection systems are not built to attract lightning. They are built to intercept lightning. There's a fundamental difference between the two. We don't wish to bring lightning that was going to land safely somewhere else into our area. But there's factors of attraction radius, the amount of energy that is in the leader of the downcoming. Let's work on the downward negative strokes. The amount of energy that is in the head of this leader coming down will dictate the overall electric field and therefore will dictate the overall stresses on the points around. So in this case, what I've just illustrated, the existing lines on this particular example is got down conductors where the arrows are going down. There are horizontal banded conductors going around the building. And when you look at the overall configuration that we have here, it effectively is a matrix of conductors parallel with each other around the building. on the one side, allowing multiple paths for the current to flow to ground. On the other side, the closer these conductors are to each other, the lower the electric fields will be that build up between the electrodes. So if we had only had a down conductor on the far left and a down conductor on the far right, the current flowing down those conductors would produce a higher electric field between the electrodes. So I'm starting to waffle now, so let me just back up a moment here and get back to the mathematics of what's happening with the lightning strike. We have in our standards that the impedance resistance of the conductor from top to bottom must be less than 0.2 ohms. So we know that resistance R from top to bottom is less than 0.2 ohms. So let's just do a calculation with 0.2 ohms. Now we have an inductance, which is 2 pi FL, as stated earlier. So we, excuse me, can determine the reactance, the inductive reactance at 2 microhenries per meter, and we still working with a 10 meters. So looking at the equations on the right hand side, I've abbreviated this, as I say, my time ran out, but in the direct comparison to the non-lightning protection system equipped building, we have a voltage of the current multiplied by the resistance of the 0.2 ohms multiplied by the 10 kiloamps gives us 40 volts, and the inductance, so it's 2 microhenries per meter, 10 meters gives us 20 microhenries. The change in current, that's 10 kiloamps, rise from 0 to maximum. It isn't quite that, but we have this value 10 kiloamps is the change in current. 2 microseconds is the speed with which it reached that maximum value. And now this issue now is because we've taken it 2 microseconds, it means that the number that we have as LDIDT is actually higher than it should be. So without the lightning protection system, looking at a faster rise time has a nice improving effect, whereas a faster rise time makes that number worse. But instead of having 200,000 kilojoules, we only have to absorb 2,040 joules. And the bulk of that current will be flowing, not the bulk, all the current will be flowing in those conductors down to ground. So just before I go to the coulombs, the essence here is that the standard says you must have at least 2 down conductors on any structure. Now, the reason for that is that you have obviously a backup, but we must have current sharing. The extent to which you have more down conductors is based on the lightning protection levels that's deemed to be directly related to the lightning current. Again, I apologize for not being able to put that up on the screen, but if you look at the highest lightning protection level, lightning protection level 1, we're looking at a minimum of 3 kiloamps. In other words, all lightning activity below 3 kiloamps will sneak through. All lightning activity above 200 kiloamps will sneak through. But 200 kiloamps is the range. 200 kiloamps down to 3 kiloamps. In order to be able to absorb those huge lightning strikes, you need more conductors. So the rationale is, remember that what I said earlier is across the country, the actual statistical distribution from 0 to 250 kiloamps is the same. Proportionally, where we have high ground flash density, the actual absolute magnitude of the lightning strikes that you count will be higher in Piet Retief than in Bellville in the Cape. Piet Retief, it will be enormous, and as a result, in Piet Retief, everybody better be paying attention. So a building in Piet Retief not having lightning protection, it needs to be explained. In Bellville, they only see lightning activity once every 5 years, maybe 15 years, depending on where they are at the time. So one can understand that one could argue from a risk perspective and how much money I must spend to protect something that only happens once every 15 years. And with that money, I could actually save enough to buy 10 or whatever it is I need, and maybe I just go and build somewhere else. The point being that our lightning protection levels in our standards specifies as lightning protection level 1. Then there's a lightning protection level 2, which is 5 kiloamps up to 100 kiloamps. and that's fine. Lighting protection level 3 is, I forget the bottom number, I think it's 8 kiloamps, whatever the bottom one is. I apologize for not remembering that, but the upper limit is also 100 kiloamps. Now, lighting protection level 4 for me is very interesting because it's 100 kiloamps. Sorry, lighting protection level 2 is 150 kiloamps. Lighting protection level 3 is 100 kiloamps, as is lighting protection level 4. But what is interesting about lighting protection level 4 is at the bottom end, all lightning strikes of less than 16 kiloamps will sneak past. What that is saying is that if you have a lightning strike with a very high electric field, it will be intercepted by the finials that you put on the roof or your mast, whatever you're putting up there to intercept it. If you have a weaker lightning strike that has a lower electric field, it will, we are safe to 5% guarantee, it will sneak past. Now, on power systems, that's okay, because there's zones of protection whereby on a shielded line, you've got a shield wire, towers that are bond those shield wires to ground. You've got your earth resistance that you still need to manage. You don't get away from that. But you've got that first pass. So when you manage that soundly, you're cutting out 90% of the lightning activity. Anything else that now is too high causes a backflash over, or however the surge arrives at the substation. First thing that happens at the substation is there is a feeder surge arrestor. Then on your feeder bay, there's a surge arrestor. And on your critical components in your substation, which is your transformers, there is a surge arrestor. And inside your transformer, you have an internal BIL of what that transformer can handle. So from a transformer design perspective, there's an internal BIL. You rate your surge arrestors directly connected to that transformer. On your bus bar, you've got surge arrestors. On your feeders out, you've got surge arrestors. And you have layers of protection. Now, that's not the case with a paper mill, a factory, numerous examples. There is not necessarily a layered approach that, we've got a backup for the values below 16 kiloamps. I'm not sure that we've got a backup for the values below the lighting protection level 3. And this is a concern, and I can apologize for pausing here and just talking as opposed to showing you illustrations. And the matter of thatch roofs, where in our SANS 10313 it says a minimum lighting protection level 3. As we tend to do with as human beings, the documentation says minimum level lighting protection level 3. Oh, good. So we will just put in lighting protection level 3. You arrive, you see a building, it's got thatch, it's lighting protection level 3. Ladies and gentlemen, that's not what it says. What it says is whatever you calculate. So before you look at it as being thatch, before you worry about whether or not it's going to burn because of lightning, before you do any of that, you do your assessments. And if you, in your assessments, find that you get a lighting protection level 4, you immediately change it to a lighting protection level 3. That's what that means. Now, so as I'm talking, if you're not picking it up, I'm kind of just wanting to share that there are some really simple facts, provided they're explained simply. And that's why I'm really disappointed that I don't have more details in this presentation for you. Future presentations and talks that will be much more detailed. But the matter is, it's really simple. And we're engineers with an electrical brain, the basics of mathematics. The issue comes down to statistics. Because it's a statistic, we cannot guarantee that we won't have a problem. Because it's a statistic, and I have to pay money to put some sort of remedial action in, I'm never certain whether I'm actually putting it in the right place. Have I done it correctly? Because unlike a water pipe pressure system, unlike the electrical energized system 24/7, you stick your finger in, you're going to get shocked. You know that it's working or not working. Lightning, you only know that your lighting protection measures is working when there's lightning. And that's why lighting detection systems are so important. Our habit of plug and play, put it in, and we'll see you later. Oh, we have routine inspections. There's so many of these units that maybe we don't get around to it. So we need to have proper support so that our engineers, consulting engineers, our insurance industry, our contractors building buildings, our architects can plan these things. Because at the end of the day, actually, when we start talking about whether we've got a lightning protection system in or not, this particular building that you see in front of you, even though it's an illustration, if it's built correctly and it's 10 stories high, it's got concrete rather than brickwork, it will have rebar in it. Have we considered using that in the design work? Is it possible to implement a more aesthetic design than what we're doing as an afterthought? At the Lighting Chapter open meeting recently, Dr. Peter Pretorius gave a presentation and raised concerns about EMC and how with surge protection, it's an afterthought. So just let me grab hold of that thought. I'm looking at the time, needing to move on. Note that when you work out the charge transferred here, it's exactly the same as the no LPS on the building. The calculation is 0.02 coulombs. In the building with an LPS, 0.02 coulombs. What this means is it proves from top to bottom, we've got water flowing in a pipe as an algorithm, as an analogy. We've got water flowing in a pipe. What's poured in the top is going to come out the bottom. If your pipe is too small, the water will back up, the water pressure will increase, and the equivalent analogy with electricity is that when you back it up, your resistance at the bottom, if it's not low enough, then back up, and it's going to start causing all sorts of voltage problems. And this is where the discussion of voltage comes in. We talk about the voltage, you know, we have enormous voltages. If you back up the pipe at the bottom of your system, trying to get this lightning current into the ground, if you back it up, you are going to get over voltages. So the next part of the lightning protection system is dealing with dangerous sparking from the lightning protection system. So when we look at a lightning protection system, an LPS is made up of two parts. Oh, sorry, that's supposed to say internal LPS at the bottom. So at the top is external LPS. It's our finials at the top, down conductors to convey the current down to ground, our earth termination system to get the current into the ground. We have a parameter in our standards that says that earth termination system must be less than 10 ohms. So again, as we understand the issue, is 10 ohms, it could be 30 ohms, it could be 5 ohms, it could be 100 ohms, whatever it is if it's not low enough, it is going to produce a voltage. If the voltage is high enough, we are going to get dangerous sparking. Sorry, so I apologize, it's external LPS, must be internal LPS. Because of the circumstances we have dangerous sparking. Now understand, when we start talking about surge protection, this is another part that needs to be cleared up across our country, is that surge protection in the context of an internal LPS is not the surge protection to protect an electronic equipment or electrical equipment in the building. The surge protection applied here is as a part of the equipotential bonding. So there's two strategies that we need to apply when we talk about this dangerous sparking that's been created by the external LPS. For starters, you don't automatically create it. Depending on how you've designed it to best install, there may be areas that you have a problem with. So in the design, you want to first look at separation distance. Have as much space as possible so that you can't get the arcing. But of course, as we have increased space, it means we have increased localized electric fields, which is undesirable. So kind of back up on that. So where we can't get the separation distance, we then go with equipotential bonding. Now, equipotential bonding is a simpler thing. You bond all the metal bits together. That's the idea. Bond everything together. So then this threat of voltage becomes nullified. If you have the same voltage on point A to point B, it means you have 0 volt drop between the 2 points and there's no current that can flow. You're safe. Equipotential bonding. So now we have the situation where the power cables can't be bonded solidly. Communications cables can't be bonded solidly. Communication cables are only an issue if I've got dangerous sparking as far as the internal LPS component is concerned. So when we implement surge protection, it's because it's a cable that carries signal. it's because we can't do anything else. Now, when we bond, as per SANS 10142-1, when we bond all the systems, the earths of different systems together, and we have to bond the lighting protection systems earth to the main electrical installation earth, what we're doing is we're bringing the voltage that is on the lighting protection system earth point into the DV of the electrical system. And so we now sit with a situation of 220 or 400 volt phase voltages that we've got to clamp. Now, the beauty of surge protection devices, it's not a diode. It's not a diode, and as an electronic guy, I like the idea of a diode. On surge arresters on the medium voltage network, it doesn't clamp the voltage at that 18 kV, whatever it is. It doesn't clamp it there. At that particular voltage is when the surge arrestor is fully open. Whatever energy there is, the 150, 200 microseconds of energy that is being transferred to ground, it's got to convey that current in 150 to 200 microseconds. That time links us back to the energy absorbed. Now, if we have other components, like the M components, continuous currents in a lightning strike, or we have multiple lightning strikes, it means that surge arrestor has to carry more energy. And again, from the data that we can access, will tell us how often we have multiple lightning strikes where our surge arresters need to be able to handle more joules. If it can't, if we see statistically our surge arresters are failing, then rather than upping the knee point and being able to, well, because it comes back to the kiloamp rating of the surge arrestor. So that's the one side. However, now when we're talking about this equipotential bonding, we do not require transfer of energy, transfer of joules. The lightning current's got its path. It's going down to ground. It is the voltage that's rising as a result of that current going down to ground that's causing a problem. So our surge arrestor needs to short the live side and the earth side, neutral side of my medium voltage or low voltage system, my communications cables. Now, hold on, isn't this a problem? Well, at 150 microseconds, let's increase 200 microseconds. My power system has got a 20 millisecond cycle. 150 to 200 microseconds it doesn't even notice it. It's a common phenomenon that we use on the shielded networks across transmission and some of the medium, the 132 kV systems, where we put a line surge arrestor across a line so that we don't allow the voltage to get to such a high value that it will flash over across the insulator and cause an air breakdown. So we put a line surge arrestor in to join the two. The moment that current flowing down the tower through the resistance at the bottom increases to a point where it's almost reaching the BIL of the insulators on that line, before it gets to that value, we have a surge arrestor there that switches on. It shorts my 765 kV phase conductor to the tower. The tower is not sitting at 0 volts. The tower is sitting at some scary, much higher voltage, 2 point whatever megavolts it is, in order to reach the BIL value, but it is only 200 microseconds. So my surge arresters start operating as high-speed switches, better than any breaker can operate. So when we want to manage our lighting, maybe we should look at surge arresters doing the switching for us. And then my comments earlier, do we fully understand what a surge arrestor is supposed to do? Then the second part, this part that's covered in SANS 62305-4, it is lighting protection of electronic and electrical equipment within a building. Now, this entire exercise, I didn't realize it, but SANS 62305-4 it's weak. It doesn't provide enough guidance for us to be able to be clear on exactly where we should be implementing surge protection measures. So we have our surge protection manufacturers guiding us, and depending on which products they think we should be using, they guide us to those products, and depending on their influence, they guide us with that influence. So we have this, we need to manage electromagnetic impulses from radiated lightning transients. We try and implement a coordinated surge protection to control our overvoltages, and we do control it by way of creating zones of protection. So in a multi-story building where a bank has a very expensive server room, that would be the highest zone of protection. And like our power system, power utility system where we've got these zones where the transformer has got multiple levels of surge arresters protecting it. The same goes for that kind of practice. But the documentation falls well short. And as a result, our SANS 10142-1, our wiring code, there is conflict as to how we need to be implementing this and going forward with it. So just talking about those standards, SANS 62305 is the adopted standards from the IEC. 62305-1 is general principles, 2 risk management, 3 is physical damage to structures and life hazards, and 4 electrical and electronic systems within structures. Now 10313 was set up as a supplementary document to part 3 of 62305 in order to be able to advance things that are unique to South Africa. Unfortunately, we've lost the plot a bit, so I will talk you through the actual where we at with the standards now, just looking at the time. On the right-hand side, we have started putting together an outline of a risk management strategy. Now, ISO 31000, SANS 31000, is a document that's all about risk management. Lightning and the threat that it poses is a risk management matter. So I'll just quickly walk you through this. The first step is, do I actually have a legitimate lightning risk? If the answer is no, our proposal is that a risk assessment report is issued. In as much as the SANS 10142-1 has an electrical COC, we need some form of assurance of a benchmark of what is and what isn't. So a healthy risk assessment that says no lightning risk, clarified, there's no lightning protection required, no lightning protection measures required. An installation safety report is issued that says no lightning protection is required. It gets, and that form is an Annex A in SANS 10313, and then that gets stored in a centralized database. If the answer is yes, the question is, do you need a lightning protection system? If the answer to that is yes, we move on to the LPS design. And there you have a SANS 62305, the lightning protection components standards, 62561. There's 7 parts to that standard, and then obviously SANS 10313. On the flip side, do you require surge protection measures? So properties that have security cameras, long lens out, and find that when there's a storm, they lose their equipment. Houses that have got thatched roofs that have got a mast and they still lose their equipment. Well, guess what? It's because they forgot or didn't understand what is actually required from surge protection measures. Now, the outcome of this is the supplement. Okay, so on the left-hand side, we use 62305 Part 3 to guide us on the surge protection measures at 62305 Part 4. I'm going to digress quickly again. The IEC standards have numerous modules that apply directly to our surge protection, but we have not adopted it because of other reasons, and they're legitimate reasons. You know, SANS 10142-1 has been legislated through the electrical installation regulations, and as a result, the way that we populate it has to be considered in methods whereby the chief health and safety inspector, when he walks in and he deems that there has been fault, that he can hold somebody accountable, knowing full well that that person has had the opportunity to obtain the necessary skills and just simply failed to do so. Alternatively, everything was done correctly and still somebody died. That is the point at which we need to step in and say, okay, well, what did we miss? That's when we step in and say, what did we miss? Not when we've run out of things to do and lack discipline and things fall over all over the place. So with every system, there is also routine inspections, and also something that has been neglected. As lightning protection systems get installed, there is a process that says it needs to be inspected and tested every 4 years, maximum every 4 years. Okay, so we have millions of installations around the country. If we started imposing that aspect of the standard, we wouldn't have enough people to be able to do the work. The demand would be so high. So we have a lot of work to do in order to prepare our South African citizens, as well as industries at large, that we have an inspection. The outcome of the inspection shows that there's defects. The defects need to be listed. The SANS 10313 maintenance certificate must still be issued. So there's where electrical COC is different. Maintenance certificate for lighting protection must still be issued. This is 4:04, and I'm gonna wrap up now. So just appreciate that there's.
Thank you.
Okay.
Sorry, time. Thanks.
Okay, can I just do a final wrap up? Okay, so for your reference later and for the audio record, all the SAN standards related to the IEC standards for lighting protection, they are all being revised right now. So please understand what is coming is going to be a lot of changes. SANS 10313 is going to be changing, but it's got to change in relation to 62305. IEC 62858 needs to be adopted in South Africa. We'll find out about that on Tuesday. We're proposing a new freestanding lighting mast standard, as well as a joint working group between the lighting industry and the fire risk industry. And then there is one standard that is not actually a standard yet, South African Technical Specification 62561 Part 8. It is not a South African standard yet, and the IEC, it is not going to be approved as a international standard yet either. Thank you, Minx. Thanks, Shepard.
Thank you. Thank you so much, Richard, for your presentation and the information. I think we really appreciate the knowledge behind the presentation. I can see that you needed more time to go through what you've shared with us this afternoon. And I know Dr. Stephen will also come in if there are any questions. We encourage everyone to please share your questions, and maybe while you're thinking about the presentation now, maybe I can ask one or two questions, and then while we're handing over to Dr. Stevens, if there are any questions, Richard. I know this is something that I was checking for one of the work that I was currently busy with. Do you know if we have a design guideline for, you know, the informal dwelling and the safety protocol for the rural community when it comes to the lightning protection design requirement? And the reason for my question is, I think you'll agree with me, most of these areas, especially in the northern side of KwaZulu Natal, that's where these are the lightning prone areas. Are there any guidelines, maybe even not for rural, but for, you know, normal residential dwelling that one can always consider? My other question, which is the second one, is the lightning strike vis-a-vis the climate changes that we are currently experiencing. Maybe just on that, if you know, there's any input that you have there. Is it getting worse, and what does that mean to the engineers? Maybe it's information that you might not have available for this presentation. And oh, sorry, the third one, and maybe I will then hand over to Dr. Stevens if there's further questions, and you can maybe combine all the answers. The third one that I've also just captured while you were doing your presentation, I mean, I'm looking at the development from the ICT space. I think there's a lot that's happening in the ICT space. Are there some requirements maybe expected in terms of now your secondary lightning protection design on sensitive ICT devices vis-a-vis your primary lightning protection device, lighting protection design, and maybe what might be the link between the two, if maybe we can touch on that. I think that these are just high level 3 questions that I have. I don't know, Dr. Stevens, can I hand over to you? Do we have any questions from the audience?
Thank you, Chair. There's none at the moment from the audience. We're still waiting for them to come up, but I've got some questions. The first one was, Richard, the issue with thatched roofs. They always had a lightning conductor installed next to the house, sort of extending above the roof. Is the question I have, is that likely to change based on your latest data, or is that still an effective measure. And then the other thing is the advent of a lot of the PV units on roofs. Would the person installing the PV units also have to take into account a lighting protection or SPM relating to the installation of the PV units? Because I think they might not be linked. I know that the PV units have inverters now installed, but whether they have efficient lighting protection, I'm not sure. So those are the two questions I have. I suggest if we can answer those from Shepherd and myself, and then I'll see if there are further questions from the audience. Thank you.
I think you muted. You unmute, Richard. Sorry.
Thank you.
Thanks.
Okay, so thanks, Shepherd and Rob. So the design guidelines for rural areas and yeah, I think in informal areas there's not a lot of structure in the buildings. It's not the guidelines that would change. It's the endeavors that we initiate, projects that we initiate to assist. You know, there's the homes, but there's also many schools and many hospitals in those rural areas that need assistance. And so it's more about us putting together policies to assist. So the matter where we start capturing reliable information with the injuries and damage to buildings out there, you know, in as much as they are informal and the communication's poor, we don't know enough about what actual damage is occurring. So when we start trying to talk about a threat risk management strategy, for me, we need to, together with government and with social services and with all the governance departments that are there, we need to put together strategies. And this is where the lighting detection data from the Weather Service and the weather management strategies from the Weather Services will be absolutely critical. So to answer the question, there is no different guideline because we're still trying to convey the same lightning current. If we would say that in those informal areas we would allow less lightning current to go through, it means that we actually biased and we are willing for those people to be at greater risk than elsewhere, and that is unacceptable. So that's my answer. In terms of climate change, we are seeing changes in the weather enormously all around the planet, and lightning is a direct majority. Lighting is a direct parameter of the presence of storm cells, thunderstorm cells. What we are seeing at the moment is a significant increase in the data that we have, but it's because we've got better monitoring systems and we're much more resolute. The South African Lighting Detection Network, from day one in 2006, there was a daily audit of that system. So when it started not performing correctly, there was immediate responses. So the Weather Service have stepped up, and then we'll be talking more about that on Tuesday. But as far as actually quantifying climate change through lighting, the tricky bit is that we have drought, we have floods, and over the 11 years they balance out. So if you go and take a number at the wrong time, wrong period in the El Nino, La Nina type cycles, and you go and measure, or you look at your performance in worse conditions, you're spending much too much money because it's going to go into a normal period and there would be no risk. The other side obviously is also an issue where you assume that you don't have a lightning problem and it's during droughts. So it's kind of like the guys in Cape Town wouldn't bother with surge protection because we don't ever see any lightning. I use the analogy of climbing into the ring with Muhammad Ali. If you climb into the ring with him 250 to 300 days a year, you're going to make sure that after a while you're so sore, you're going to put in proper protection. Whereas down in the Cape, 3 days a year, you don't really notice because you got beaten up in 3 days. But if you start looking at how many times the storm actually came through and how much your system actually was protected, you find out that it's almost nothing. And so in terms of climate change, it's way too soon for us to be able to properly say it, because the detailed lighting detection system has only been running since the end of 2005. So we are now going into the second cycle. And I think it's, Mornay Gibbon and the guys from the South African Weather Service, scientists with guys from BITS University and others from other universities around the country, are looking into all the weather patterns and looking into the impacts. So what I believe will happen is that our lighting data will come afterwards. As we kind of be expecting the lighting data to increase, and when we see it increase, we say, check, we were expecting it. And in a way, we would then also be confirming that our lighting detection networks are working. So, yeah. Okay, then in terms of the ICT space, it's surge protection measures. Again, the policies are no different. What is missing in our standards is not having enough clear guidelines that it becomes currently there's still too much ambiguity. I think if anything, the ICT guys and the networking guys are more aware of doing the right thing than the rest of us are. Rob, freestanding lighting masts are here to stay. It is a strategy whereby it's the fire risk managers that have said that they don't want lighting anywhere near the thatch for risk of causing fires. What is the problem is the condition of masts being installed that they're not adhering. And currently we've taken the easy road and just adopted the lighting mast standard, which is SANS 10225, and it was never intended as a normative document, and now people are trying to implement it as a normative document, and that's causing huge problems, with the implication of suggesting, you know what, lighting masts are a thing of the past. There is an alternative, it's an excellent alternative, but currently the science has not been proven, and we sit with the risk that when the bathtub curve starts going up, we're going to have hundreds, thousands of houses, buildings at risk if those devices start failing. And then as far as the PV installations are concerned, again, it falls back on the fundamentals are there. When you need to protect against over voltages and surges, you need to put those devices in. You know, that's a straightforward electrical and electronic aspect that needs to be properly documented. And that's where 62305 and the other IEC standards that I'm going to be looking to support that we adopt them will help us through that path.
Thanks, thanks, Richard. Maybe let's check with Dr. Stephen if we can give you extra 2 minutes, Richard, for a question or so. Do we have some questions, Dr. Stevens? Thanks.
Yeah, we got 2 questions from Robert and Stuart. The one is, would a building residence close to tall trees like gum trees provide satisfactory LPS in terms of protecting the building itself from high levels of lightning discharge, sort of like a gum tree acting as a steel pole?
Yeah.
And the second question, I think you might have answered, but it's slightly different on the PV. He said that there is, of course, PVs come with earths installed, but are these earths conductors suitably rated for lightning discharge current? So those are the 2 questions we have.
All right. So tall trees near buildings cannot be used as a, so I guess there's 2 ways to look at it. Tall trees near buildings cannot guarantee that you won't have a problem. What we do know is don't go and stand underneath a tree when there's lightning, because trees and wood are not good conductors. So the issue where the joules absorbed, like I mentioned, what happens with wood is that you've got this huge amount of charge rushing into this wood. It's not a good conductor. It starts absorbing this extra energy, and the energy converts to heat. Heat expands, and the tree splinters and blows up. So the first part is shrapnel. There's a number of injuries that one can get from lightning, and one of them is being hit by shrapnel. So that's obviously not a good thing. So using the blue gums and the tall trees near your house as a protection measure, it's not good. The second part is that if you're too close, you stand a risk of a flashover. So step potential is almost, you're close enough that the electric field is such that the front end of this surge sees your body as a better conductor than the tree into the ground. So so the flip side of it is if you've got a lot of trees around your property, what does happen is that you now have many elements. It doesn't matter that they're not good conducting. The charge, the opposite charge, if the cloud is negatively charged and you've got a negative downward leader, the positive charge in the ground rushes up to the top of these trees. The fact that you've got this charge across an entire area just means that the upward streamers, so if you had a single mast sticking out amongst these trees, that mast would be metal, it would be ready to conduct, and it would have a higher local electric field than the trees would. So as a nice, I guess, warm and fuzzy feeling that you've certainly got a lower probability of getting hit by lightning your home than if you were out in the desert or in flatland, in Bloemfontein somewhere where there's no hills, no trees, nothing else. So yeah, it's not a guarantee. And when all of this stuff that we're talking about is where there is a real risk that somebody could get injured, you could have a loss of service. You know, the filling station at the Kruger National Park is a loss of service, and that hasn't been looked at properly. So there's a number. And then obviously the third is your economic losses. If there is really a low risk of losses, it's fine. And then the PV systems, as far as using the earthing of those systems as a lightning down conductor, it's not a good idea. The ideal, remembering that it is there, but those things are bonded to the chassis of the PV panels. And if we wanting to allow the lightning strike to terminate on the panel, there's many samples of how the edge of the panel has been totally destroyed because of the mechanical energy. We talked about the 200,000 kilojoules. That's what causes the mechanical damage on PV panels. So it's not a good idea to. It is more sure if you provide a dedicated, separate path off the panel to the common earth.
Thank you, Richard. Thank you so much, Dr. Stevens, for assisting us with the question and answer session and for partnering with us in driving this. And I can sense from the discussion, Richard, that I think you will actually need a day to take us through the information. There's a lot that you know, I see you wanted to share with us this afternoon. And also I can note that you're welcoming more hands to join you in this discussion chapter, and that I see there's also a lot of information that you're still working on. But I must say, from the KZN Center, thank you so much for this information that you've shared. I'm sure that the audience also have benefited from these discussions this afternoon. So we're looking forward to also seeing you soon in the KZN Center. And I'm sure whatsoever that we have been touched this afternoon will be presented at our next discussion. And we thank you one and all for your participation and for dialing in this afternoon. And we encourage you to please visit our webpage at www.SAIEE.org for future webinars. And we thank you for joining this afternoon. The webinar is closed. Thank you. Enjoy your evening.